All right, we're going to take some notes on the area under a curve. And to look at this and how we're going to work with it, we're actually going to look at a specific example to get started. So we're going to say, given the equation y equals x squared, we want to estimate the area under the curve. On the interval from 0 to 1. And when we say under the curve, what we mean by under the curve is between the curve and the x-axis. So between curve and x-axis. Okay, so let's go ahead and draw a sketch of what it is we're trying to find. So I'm looking at the interval from 0 to 1, and I know that if I graph this, 0 squared is 0, and 1 squared is 1. And so there's the right side of my parabola. I know the other side's over there. And I'm looking for the area under the curve, and so I'm looking for this part right here. I want to find that shaded area right there. So what I want you to do is go ahead and pause the video and write a prediction about what you think the area of that curve, underneath that curve, could be. And you're probably not going to be able to get the exact answer right away, just make a good prediction. So if we think about this square right here, the area of this square would be 1 by 1. So that has an area of 1 unit. So if we're making our prediction should be somewhere between an area of 0 and maybe an area of half. If you can see, if I were to draw this, my shaded area is a little bit less than half of the entire area of that square. So that's somewhere we're going to expect the actual area to be somewhere in between there. So we have a couple different ways of approximating the area, not getting an exact answer, but getting an approximate answer. And one is to use 4 rectangles to find the area. And we're going to use their right endpoints, which will make sense in a second, as the heights. So I'm going to go ahead and draw this picture again, and we are going to be drawing this a few times. So I'm going to say, if I take this drawing and I divide it into fourths, then I can find the area of this if I divide this picture into little rectangles. So I'm going to take this is 1/4, and I'm going to draw it up to the line and then draw it over and find the area of this rectangle. And then I'm going to draw this one up to the line and over, and I'll find the area of this rectangle, sorry. Draw this one up to the curve and over, and I'll find the area of that rectangle. Draw it up and over and find the area of that rectangle. So as you can see, it's going to help me find the area underneath the curve, but I have a little bit extra and a little bit extra and a little bit extra, so this is going to be an overestimate for how much area I have underneath that curve. So here is our notation when we do this. We're going to say this is using the right endpoints, and you'll see in a second the difference between right endpoints and left endpoints. And we're going to say that the area of the first rectangle would be 1/4 is the length of the bottom, and then the height of that rectangle is whatever I would get when I plug 1/4 into that equation. So the equation was y equals x squared, so it'd be whatever I get when I plug 1/4 into x squared. Then the width of the next little rectangle is also 1/4, and the height of the rectangle happens where the x value is 1/2. And so I'm going to plug 1/2 into that equation to see what the height of that rectangle is. The width of the next rectangle is still 1/4, and the height of this rectangle I would get by plugging 3/4 into the equation. And then the width of the last rectangle is still 1/4, and the height of the last rectangle is a value of whatever I get when I plug 1 into the equation. All right, now there is a shorthand way to write this, so we don't have to type all of that into our calculator. So we're going to think of 1/4 as being kind of like the GCF of this problem. So we're going to put 1/4 in the front. And then we're going to say we've got 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared. And we're going to talk about it more later, but this is called a Riemann sum. We'll reference that later, a Riemann sum. So if you multiply all that out on your calculator, what you're going to get is 0.46875, which is the same as 15/32. And like we already said, this is an overestimate because our little rectangles went above the curve. So that's an overestimate. Okay, next we're going to go ahead and we're going to use 4 rectangles again. And this time we're going to use the left endpoints. So we're going to draw the picture. And I'll divide this into 4 pieces. Now we'll zoom in so you can see what I'm doing. Okay. So this time we're still going to be drawing these rectangles, but we're going to use the left endpoints. So this first one doesn't really get to be a rectangle right there. Then this is the endpoint that we're going to make the rectangle on next. And then this is the next rectangle. And this is the next one. So if you look at this one, this is going to be an underestimate, so we're still building these rectangles. You can see with the right endpoints, if you did the right edge on the curve, then when we make the rectangle, it goes above the curve. On this one, if we had the left side of the rectangle on the curve, then it goes underneath the curve and we have some free space that we're not actually calculating in our area. So this is going to end up being an underestimate. So let's go ahead and write out our sum, adding up all those rectangles together. So this time we're going to say L sub 4, and the first width is 1/4, and the height of that rectangle is actually 0. You'd get it from plugging in 0 because that's the part of the curve that it's touching. The next one is also going to have a width of 1/4. And the height that we're using right here is this x coordinate of 1/4, and it's whatever y value we got when we plugged 1/4 into the function. And then this next rectangle, I don't know why I keep confusing those two words. The next rectangle also has a width of 1/4, and the height of this rectangle we would get by plugging 1/2 into the function. And then the last one also has a width of 1/4, and we would get the height of that one by plugging 3/4 into the function. So I'm going to say that if I want to calculate this and plug less numbers into my calculator, make my life a little bit easier, I can take out that 1/4 that was in front of all of these sets of parentheses, put it in the front. And that makes my life a little bit easier when I plug it in my calculator. And when you plug this in, you should get 0.21875, which is 7/32. And that would be an underestimate, and we can see that it's an underestimate because our little rectangles don't take up all the space that was underneath the curve. So using the right endpoints and the left endpoints as heights are 2 ways to find an estimate of your area. You might look at this and say like, oh, maybe we should average those two things. If one's an overestimate and one's an underestimate, then maybe we can get one that's kind of in between. So if you do 15 over 32 plus 7 over 32 and divide that in half to average it, that gives you 11 over 32, which is 0.34375, and that is closer to the actual answer, which I know, but I'm not going to tell you yet. It's a lot closer to the actual answer, but it's still a little bit off. It's actually still an overestimate. So there's one more method that we can use when we're finding the area of these rectangles, and that other method is to still use 4 rectangles. And this time we're going to use the midpoints as height. So again, we're going to go ahead and draw this picture. Find those evenly. Okay, so this time, when we make our little rectangles in here, we're going to make the height of the rectangle based off the midpoint, where the midpoint hits the curve. So the midpoint of the first one is about right there, and I'm going to build a little rectangle with that. And then there's the midpoint of the second one. I'm going to make a little rectangle. And here's the midpoint of the third one, sorry. I'm going to make a little rectangle. There's the midpoint of the last one. I'm going to make a little rectangle. And what you'll notice is that when you do the midpoint version, you go a little bit above the curve, but also stay a little bit underneath the curve. So they kind of balance out as they go. It's not a complete overestimate or underestimate because you're kind of doing both at the same time. So again, we're going to go ahead and write down the sum of these rectangles. So I'm going to say m sub 6 for midpoint. The width of each of these rectangles is still 1/4, but the height is going to be calculated a little bit differently. So the height is calculated based off the middle of these two numbers being plugged into the equation, because the height comes from where you intersect the curve. So for the first one, the middle of 0 and 1/4 is 1/8. For the second rectangle, the width is still 1/4. The height is going to be the middle of 1/4 and 1/2. Gosh, which is 3/8. That hurt my brain. The third rectangle is still a width of 1/4. And this one is going to be 5/8. And then the last one, the width is still 1/4, and the height would be what you get when you plug in 7/8. So I can go ahead and rewrite this so it's easier to plug into my calculator. And what you get on this one is you get 0.328125, which is 21 out of 64. That's a pretty good estimate there. It's not the exact answer, but it's pretty stinking close. So if you think about this method, how could we get an even more accurate answer? And the answer to that is to use even more rectangles, to use skinnier and skinnier rectangles, because then they're not going to go above and below the line as much because they'll be more narrow, or they won't be quite as wide. So if we had 100 rectangles instead of 4, our decimals would probably be more accurate than what they are right now. So for this problem, the actual area is 1/3. And you can see we were pretty stinking close right here. So the actual area of that is 1/3. And we don't have the math yet to really show that in an easy way, but that's something that we will build towards. That's the next thing that we're going to be studying in calculus class. So now that we have looked at that example, we want to write the mathy stuff out. So here's the definition of what we're doing next. So it says the area A of the region that lies under the graph of a continuous function on the interval AB is, so, and when they say under the graph, they mean exactly what we did as far as looking at the curve between, or looking at the area between the curve and the x-axis. So that's what they mean by saying under the graph. And it is the limit as n approaches infinity of the change in x. And so when they say this delta x over here, or the change in x, we're looking at these little pieces right here. So this is kind of like saying this number in the front, this 1/4. So if I divide it into 4 pieces, it's going to be like 1/4 of the total distance between them. If I divided it into 6 pieces, it'd be 1/6 of the total distance, that sort of thing. So we're saying that, and then we are multiplying that by the summation. And that's what we did here, is we were doing a summation. We were taking a pattern of numbers and we were adding them together. So that's a summation of f of x sub I. So this is the formula, and I'm about to define what each of those things are. So this is called the limit of sums of areas of rectangles And when we do these problems and we're not saying as n approaches infinity, we just say that the n is 4, or like in this case it was 4 because we only had 4 of them, or the n is 6, or the n is 10. That would be a Riemann sum, we were talking about earlier. Okay, so here the way that you figure out what your delta x is you take your interval and you find the distance between the 2 points. So we'll do b minus a divided by n, where n is the number of triangles you're making. Sorry, number of rectangles. Goodness gracious. Okay, number of rectangles. There we go. X sub I is whatever fraction you get for delta x, or whole number you get for delta x, whatever that happens to be, multiplied by I plus the a value. So this is essentially saying start at a, and then whatever it needs to change by each time. So like we did 1/4, then 1/2, then 3/4, then 1. And so that's what we got when we just added 1/4 each time. So those. And those are the things that you're going to be calculating when you find this. All right, so for example, I'm sorry, I'm kind of hesitating because I know that this is a little bit confusing. The notation looks really weird. We're going to work with the notation. We'll get to the point where it's a little bit less confusing. So I'm just trying to figure out how best to explain it in a way where you guys won't be as frustrated to start with. So go ahead and we're going to do this example and then we'll be done. So write the area under y equals x squared on 0, 1 as a limit. So we're going to find our delta x first, and we're going to say that is b minus a divided by n for the number of triangles, number of rectangles, oh my goodness, which is just 1/n. And then our x sub I is going to be 1/n multiplied by I plus the lower end of our interval, which is 0. And so this we can just call I divided by n, or 1i divided by n, however you want to write it. So now if we use that definition of how we write the limit, we're going to say the limit as n approaches infinity, and then it's going to be 1/n multiplied by the summation from 1 to n of I/n squared, which is kind of interesting, weird notation, but this is just a really fancy way of saying exactly what we wrote up here.